Hello everyone, welcome to Merrimack STEM Academy. Today we're going to talk about intermolecular forces. IMFs are so important for chemistry and biology, but they're commonly misunderstood. One of the most common misunderstandings is what IMFs actually are. To clear that up, we need to talk about the difference between intramolecular forces and intermolecular forces. Intramolecular forces are chemical bonds within a molecule. For example, a covalent bond between two oxygens in a molecule is an intramolecular force. Ionic bonds are also intramolecular forces. On the other hand, intermolecular forces are attractive forces that exist between molecules. For example, these two water molecules are attracted to each other and there is a hydrogen bond between them. Notice that the intermolecular forces exist between two or more molecules, whereas intramolecular forces exist within one molecule. Now, intramolecular forces are true chemical bonds, and they're generally stronger. Intermolecular forces are the result of electrostatic attraction, which is positive and negative charges attracting, and IMFs are typically weaker. To understand IMFs, you first need to understand polarity. Polarity occurs when electrons are unevenly distributed in a molecule. In hydrogen fluoride, fluorine is much more electronegative than hydrogen. So, fluorine will pull electrons toward it. The electrons will spend more time near fluorine than near hydrogen, creating an uneven distribution of electrons. As a result, fluorine will have a slight negative charge because it has more electrons near it. Hydrogen will have a slight positive charge. This is not a full negative or positive charge like in an ion. Instead, it's a partial charge. Let's take another look at the water molecule we mentioned earlier. Oxygen is more electronegative than hydrogen, so it will pull electrons toward it and have a slight negative charge. The hydrogens will have a slight positive charge. Each molecule has a negative end and a positive end. This is called a dipole because the molecule has two poles. One is slightly negative and the other is slightly positive. Just because a molecule has polar bonds doesn't necessarily mean the whole molecule is polar. Let's take a look at a covalent bond between boron and fluorine. Fluorine is more electronegative than boron, so this is a polar bond. Boron trifluoride has 3 bonds between boron and fluorine. However, the electrons near boron will be pulled toward the fluorines in 3 opposite directions. This means that the attraction from the fluorines will cancel each other out. As a result, the molecule is nonpolar. To make sure a molecule is polar, first check to see if it has polar bonds. Then, check its molecular geometry to make sure the molecule can be polar with its shape. We are going to go through the different types of IMFs involving polar and charged molecules from weakest to strongest. Dipole-dipole interactions exist between polar molecules. For example, in formaldehyde, oxygen is more electronegative than carbon, giving oxygen a slight negative charge and carbon a slight positive charge. As a result, the partially negative oxygen in one molecule will be attracted to the partially positive carbon in another formaldehyde molecule. This is a dipole-dipole interaction. Similarly, with hydrogen chloride, chlorine will have a slight negative charge and hydrogen will have a slight positive charge. There will also be dipole-dipole interactions between these molecules. Next, there are hydrogen bonds. Some people call these interactions hydrogen bond force, which I think is a good idea because hydrogen bonds are not true chemical bonds like ionic and covalent bonds. Hydrogen bonds are a type of intermolecular force that exists between polar molecules. Bonds between hydrogen and nitrogen, hydrogen and oxygen, and hydrogen and fluorine are very polar because nitrogen, fluorine, and oxygen are really, really electronegative. Hydrogen bonds are like dipole-dipole interactions, but stronger because they involve more polar bonds. Water has bonds between oxygen and hydrogen, so it can form hydrogen bonds. Hydrogen fluoride has bonds between hydrogen and fluorine, so it can form hydrogen bonds as well. On the other hand, hydrogen chloride only has HCl bonds, which are less polar. This is why hydrogen fluoride can form strong hydrogen bonds, but hydrogen chloride can only form weaker dipole-dipole interactions. An intermolecular force stronger than hydrogen bonds is an ion-dipole interaction. A dipole is a partial charge, but an ion has a full positive or negative charge. If you increase the charge, the intermolecular force will be stronger. For example, water is a dipole, and an ion-dipole interaction forms between water and ions like the sodium and chloride ions. This IMF is what makes water such a good solvent and allows it to dissolve salts. The strongest intermolecular force is ion-ion interactions, which occur between two ions. In sodium chloride, there is an ionic bond between the sodium ion and the chloride ion. These interactions between multiple sodium chloride ions will form a grid-like structure of alternating sodium and chloride ions. This is called a crystal lattice structure. At this point, we've talked about polar molecules and ions. You may be wondering, what about nonpolar molecules? Yes, nonpolar molecules do interact. The name of this interaction is van der Waals or London dispersion force. The names are used interchangeably, and they describe the same force, but I'll be using the term London dispersion force because that's what I was taught. London dispersion force is found in all particles, whether they are nonpolar molecules, polar molecules, or ions. While polar molecules and ions usually have other stronger interactions, when nonpolar molecules interact, London dispersion force is their only intermolecular force. Let's look at an example. Cl2 is nonpolar because each chlorine has the same electronegativity, so they will share electrons evenly. However, the electrons are constantly moving around in the molecule. So, maybe at one moment, more of the electrons happen to be near one of the chlorines, creating a temporary dipole. At this moment, because of the dipole, the molecules may be attracted to each other. Electrons are constantly moving, so the next moment, the dipole may change. This is a weak temporary dipole, unlike the permanent dipole in a polar molecule. Because London dispersion force involves temporary dipoles, it is the weakest intermolecular force. Let's take a look at all the intermolecular forces we've talked about. London dispersion force, dipole-dipole interactions, hydrogen bonds, ion-dipole interactions, and ion-ion interactions. The particles involved in each type of intermolecular force are also shown. As the strength of the intermolecular force increases, so does the magnitude of the particle's charge. The weakest force, London dispersion force, is the only interaction between nonpolar molecules. Nonpolar molecules have no charge. The slightly stronger dipole-dipole interactions involve polar molecules, which have a dipole, partially charged regions. Hydrogen bonds exist between really polar molecules, which means the magnitude of the charged parts of the molecule increases. The strongest intermolecular forces, ion-dipole and ion-ion interactions, involve ions, which have a full charge instead of a partial charge. So, you can see how as we increase the magnitude of the charge, the type of intermolecular force is stronger. Now that we know the types of intermolecular forces, how do we identify the forces present in a pure substance? First, we need to ask if the particle is nonpolar, polar, or charged. If it's nonpolar, the only force present must be London dispersion force. If it's polar, then you must determine if the molecule has NH, OH, or FH bonds. If not, then the intermolecular forces present are dipole-dipole interactions and London dispersion force. If the molecule does have these very polar bonds, then it can form hydrogen bonds as well as London dispersion force. If the substance is made of ions, like a salt, then it has London dispersion force and ion-ion interactions. We've talked about the different types of IMFs, but so what? Why do they matter? Well, intermolecular forces have a big impact on the chemical properties of a substance. Let's talk about a few of these properties. First, viscosity, which is basically how thick a substance is. Think about pouring water versus pouring honey. It's much easier to pour water. Intermolecular forces and viscosity are directly proportional. More viscous substances have stronger intermolecular forces. Surface tension and intermolecular force strength are also directly proportional. Water has pretty strong intermolecular forces due to hydrogen bonding, which gives it a relatively high surface tension. As a result, some small insects can walk on water without breaking these hydrogen bonds. It's also what allows you to float a paperclip in a cup of water. Capillary action is when a liquid can move upward against gravity. As intermolecular forces increase, capillary action decreases. They're inversely proportional. A common example of capillary action is the curve of water in a graduated cylinder, which is called a meniscus. The water has stronger adhesive forces to the walls of the glass beaker than it does to the other water molecules. The interactions between two different substances, like glass and water, are called adhesion. Cohesion involves interactions between molecules of one substance, in this case, water. Capillary action is also important for how water is able to travel up the stems of plants. Vapor pressure is how easily a substance can become a gas. To become a gas, all the intermolecular forces must essentially be broken so the molecules can move about freely. If a molecule has stronger intermolecular forces, it will take more energy to disrupt these interactions, so it will have a lower vapor pressure. This means that the substance will have a higher boiling point, as more energy is required to disrupt the intermolecular forces. For example, salts like sodium chloride have strong ion-ion intermolecular forces, which means they have a really high boiling point. Think about it, when have you ever seen gaseous sodium chloride? Hopefully never, because it has a boiling point of 1,465 degrees Celsius. I just threw so much information at you, so let's take a second to review everything we've talked about. No new information here, I promise. The strength of the intermolecular force increases as the charge of the particles involved increases. The weakest IMF is van der Waals or London dispersion force. It is present between all particles. Next, dipole-dipole interactions involve polar molecules, which have a slight positive and a slight negative charge, creating a dipole. Hydrogen bonds are like dipole-dipole interactions, but they involve really polar bonds, NH, OH, and FH. Ion-dipole interactions exist between an ion with a negative or positive charge and a polar molecule. Ion-ion interactions exist between a positively charged ion and a negatively charged ion. Molecules with weaker IMFs, like London dispersion force, will typically have greater capillary action and high vapor pressure. Substances with stronger IMFs will most likely have a higher viscosity, surface tension, and boiling point. Are you ready to put your knowledge to the test? Answer the following questions about the molecules listed above. Pause the video here and see what you know. Alright, let's talk through this problem. Potassium bromide is a salt that contains the potassium ion and the bromide ion. So it will have ion-ion interactions and London dispersion force. Methane only has nonpolar carbon-hydrogen bonds, so it's nonpolar. The only IMF present is London dispersion force. Ammonia is polar and it has really polar nitrogen-hydrogen bonds, so the answer is London dispersion force and hydrogen bonds. Last but not least, hydrogen chloride. It's polar, but it can't form hydrogen bonds like ammonia. Hydrogen chloride has London dispersion force and dipole-dipole interactions. Next, we need to rank the molecules by the strength of their intermolecular forces. To do this, we're going to have to think back to our list of the types of intermolecular forces ranked by strength. Methane would have the weakest IMFs, then hydrogen chloride, then ammonia, and potassium bromide would have the strongest IMFs. Finally, we have some questions about chemical properties. High surface tension is associated with strong intermolecular forces. Potassium bromide has the strongest intermolecular forces, so it will also most likely have the highest surface tension. It's the opposite for capillary action. Capillary action involves adhesive forces between the molecule and another substance, like glass, so we're looking for the molecule with the weakest IMFs, which is methane. Next, vapor pressure. Weaker intermolecular forces are easier to break, meaning it is easier for the molecule to become a gas. So, again, the answer is methane. The molecule with the highest boiling point will most likely have the strongest IMFs, because it will take the most energy to disrupt these strong IMFs. This is potassium bromide. To show that IMFs really do influence chemical properties, let's look at how IMFs affect boiling point. The 4 molecules are listed from weakest to strongest IMFs, and their boiling points are shown. You can see that IMF strength really does indicate boiling point. And on that note, you've made it through the video. Thank you for listening. If you found this helpful, please like this video and be sure to let us know in the comments what topic you want us to explain next. And subscribe for more videos about chemistry, biology, and everything STEM related.